the idea of RMSprop was developed by Geoffrey Hinton, and it's not written on a paper or something. When he was teaching in his lecture notes, he came up with this idea, and he taught it for quite some time. And then people in his lecture notes noted that this is really working when deep learning somehow got a thing. So what is the idea there? What he says, he somehow interpreted this RProp to be a kind of, just wrote an alternative form for it. And then he saw that basically the whole challenge we saw there is because of high variance of the samples, right? Because in this example I told you, we said that this 0.1 could be also negative if we just sample once again, right? And, well, this is because of variance, right? So he wanted to reduce the variance. And the idea was that, OK, I have lots of a sequence, so maybe I compute a moving average. So now, this way, it just somehow stops ignoring completely the magnitude of the gradient, which is being done in the RProp, or the basic form of the RProp. So what is the idea here? The idea is that you can write down the RProp in this form, right? Everybody agrees? So if you are in one particular iteration, t, you only look at the sign of the gradient, right? Every single entry, you look at the sign. Then you already have scheduled this eta t using your scheduler, the RProp scheduler, which is just deciding based on the sign, right? And then you multiply every single learning rate to its corresponding sign, and then you move, right? So this is what you do in basic RProp. Everybody agrees, right? Now, I can write this thing down equivalently in this form, right? Instead of sign, I can write gt, this is the gradient at time t, divided by amplitude of the gradient at time t, right? Everybody agrees? So this is a vector operation, right? Absolute value, right? It's the absolute value, exactly. Like, no, sorry, not the norm of the gradient. No. The amplitude at every single entry. It means that, I mean, what you do is, OK, that is a bad notation. So, this means that, say, your gt, is -1, 3, right? And then the sign is going to be, you're going to write the sign of gt. This is going to be -1, 1, right? Right? So you could write it down equivalently, -1, 3, divided by entry-wise, the amplitude, which is 1, 3, right? Right? -1 divided by 1, 3 divided by 3 is going to be -1, 1, right? So entry-wise division here, right? OK. That's clear, right? So, yes, question? This. Sorry, sign has what?
So sign gt does not have any direction in it, right?
No, it's a vector of -1s and 1s, right?
Yes.
OK, and then this is one direction, right?
Okay.
Yes. You are doing that, and then for the amplitude of every single entry in this vector, you just rely on your learning rate, right? This eta is not a number. It's a vector again, right? So you have two-dimensional case for the example on the board. You have -1, 3, right? Then the sign is going to be -1, 1, right? But you already have done this update of learning rate for every single dimension separately, right? Maybe learning rate for the first one is 0.1. For the second one is 0.8, right?
So the exact direction is set by the learning rate.
Exactly. This is what we did in RProp. We just relied on the sign, because we said sign is telling us for every dimension where we should move, right? And then how exactly we should scale it, we just relied on the learning rate, right? But this made the issue with the mini batches, because the mini batch is very changing. Then the sign could easily change, and I could just totally get lost. OK? OK. So yeah, you can write this down in this form, right? And one thing that I, again, should mention, this eta now is a vector, right? So this eta t is a vector of learning rates, right? So every single dimension, you have done it separately, right? Now, what Geoffrey Hinton was looking into was that, OK, we are just doing averaging, doing normalization by the amplitude of the gradients, right? The absolute value of every single gradient, right? But this absolute value is quite noisy, right? Because you are doing mini batches, right? And mini batches could just sample with high variance, right? So what you can do to reduce this variance, you can replace this guy with the moving average, right? That was the only idea. So this is what we do. So we do that. The root of the problem is the variance, and then we just replace the denominator by the moving average. So how we can do it, say I have this vector v, okay? And what does this vector v does? I mean, if you start from 0, the first time you are having gt squared, right? Amplitude of gt is squared. And again, that amplitude, that absolute value of gt is a vector, right? So looking at this example I have here, what is the absolute value of gt squared? 1, 9, right? So it's a vector, 1, 9. That is the red vector here squared, right? So you have that one. You start from value 0. You just compute the moving average every single time step, right? So you start from 0. The first guy is exactly the amplitude is squared. The second one is the first absolute value squared average with the second one. The third momentum is going to be the first, second, and third amplitude squared average, and so on, right? So in every time, you're just averaging over all the iterations you had, and because of this, you are getting less variance. Yes? Sorry? Why? Yeah, I mean, you can drop it. That's square, right? It's not a big deal, right? So, yeah, I mean, that doesn't make any change, right? Okay. So, now you are doing this, and by doing this, you are just reducing the moving average of this guy, right? Now, when you want to update, instead of updating as before, so here we initially said that we have gt divided by absolute value of gt, right? Now you just replace square root of your momentum, right? The momentum you computed, this v guy, right? So again, if you set beta equal by 0, what's going to happen? You're ignoring all the previous momentums, right? And the only thing that you pay attention to is square root of, square root of the gradient, right? When you replace it here, it's going to be, again, the absolute value. This is exactly the same form that you had in the RProp. Everybody sees that? OK. Now, one thing that you can benefit now from is that you can stop updating this eta, actually. Because that eta getting updated is somehow incorporated into this moving average. So you can drop. You can keep eta to be fixed. So you don't use this scheduler anymore. You can do it. You can keep the scheduler. It might, in some cases, help. In some cases, it might not, right? But the classic practice is that you just drop the scheduler, right? You just fix that one, and you would say that the learning rate scheduling is still being done, but it's being done by this root mean squared, right? That is what the mean, the root of this momentum v is. Everybody's clear? Questions? So that is eventually reducing your variance using this sort of second order momentum of the gradient. OK, so basically what we are doing in RMSprop, we are basically using, again, somehow we are doing learning rate scheduling, but our scheduling is somehow inspired by the RMSprop, right? So again, if you look at this guy here, eta divided by this one, this is still dimension dependent, right? So for every single dimension, you are getting different value of this, momentum, right? And then you scale your learning rate with that one, right? But this is much easier and much less variant as compared to the basic RProp. OK, so classical choices again. So if you want to just choose beta here, you again need to choose it close to 1. Typically, you choose it larger than the beta you use for your first order momentum, that m in the momentum approach. because here you are squaring everything, right? So you want to just make it closer to 1. So yeah, 0.99 is a classical choice. You just give it a very close number to 1. Basically, you are just taking a tiny bit of your new gradient. You keep everything in the moment, right? OK, so you can access this one again using PyTorch. So it's already implemented in most available packages. And last but not the least is the atom, right? The atom, which is the one everybody uses nowadays, right? So what does atom do? Basically, atom takes the idea of first order momentum m and the RMSprop, and then use both of them together. That is atom, right? This is why in atom you have 2 different momentum coefficients. So what does atom do? I mean, the name is adaptive momentum estimation, ADAM, right? So and you can guess that the abbreviation was somehow with some purpose, right? Because atom sounds nice, right? And interesting thing is that the original paper is actually a preprint, a white paper. You can find it on a preprint on archive, but it has been like hugely cited. And the main idea, as I said, is they're going to use both the approaches. So RMSprop is just using the second order momentum. The basic one is just the basic momentum uses the first order momentum, and it says like if I want to reduce the variance of the direction of the gradient and the variance of the scheduling that I'm doing on the learning rate, I can use both the momentums together. I mean, of course, the paper is not just simply saying that use both of them together. It does some analysis to show that this is very efficient in terms of convergence, but this is the main idea. So you use momentum for updating the weights, the basic momentum, and then you use this other second order momentum to do your scheduling, and this is how the atom going to look like. So you're going to start from 1 first order momentum, 1 second order momentum. Typically, you start with a very small number, close to 0. And then in every single iteration, you are going to update your momentum. So you're going to say that whatever my gradient was, that gradient is going to update the previous momentum using this kind of moving average. And this other second order momentum v is getting updated with the second moving average. And at the end of the day, if I want to update, I am going to update using this scheduling, this normalization with the second order momentum. And then I move in the direction of the momentum, right? That's it. Everybody's clear? Yeah? Yes? RMSprop, there you don't use M, you use G itself, right? The only difference is that one. Right? Questions? Yes? We typically initialize them with something very small. Like this V, you cannot put it 0, because this is going to make you into trouble. Like in practice, you start with some epsilon, and then at some iteration, you're going to drop that epsilon. So I mean, not that epsilon. I mean, you start here with 0, but here in denominator, you're going to add a bit of tiny perturbation, like epsilon. And then you drop it at some iteration on. Yeah. Questions? Yes?
How much better is this?
Significantly better, yes. This is why nowadays everybody uses atom, right? This is really helping, right? Especially when you are doing small mini batches on a huge data set. Yeah, this is going to do a lot. Yeah. Because one thing that you should pay attention, like if you think about the real data, like a very high resolution image, right? And then this guy is having like C4 100. You have 100 different labels, right? Now if you take one mini batch of size 64, okay, definitely within that mini batch you don't have all the labels, right? So that gradient is significantly different from the true gradient you can think of, right? Because it's not even averaging over one label, right? Whereas that one is averaging over everything. In low dimensional case, you don't see it. But when you increase the scope of the problem, then those sample gradients can be hugely noisy. And because of that, this one is going to help a lot. Yeah. Questions? So now, one thing that you should pay attention, whatever we discuss here, we wanted to get the idea. So this exact pseudocode, there are some numerical tricks to make them stable. So if you really want to implement that by yourself, you need to take a look on the papers that develop these ideas, right? So there are some tricks. There are even complementary files where they explain how you can implement them. But obviously, I mean, nowadays in practice, most people just use the packages, right? Old days, people had to implement that one by themselves, right? They had a library written by them, like the first function is Atom, the second one. And then if it doesn't work, you need to go inside that to check why it's not working. Maybe a problem is inside the Atom implementation. Nowadays, we don't have those troubles, right? So yeah, typical choices for beta, 0.9 is the one you use for first order momentum. Second order, of course, you are going to increase it more, right? Because you take the square root. Because of that, you use larger value. You usually take both of them very close to 1, right? Because it's going to reduce the variance significantly. And yeah, that was it about the different optimization approaches or different optimizers. So the key point is that you're always using a stochastic gradient descent. But that is stochastic gradient descent. You just modify it. And this modification, as you have seen, is basically relying on 2 factors. One of them is that you want to just schedule the learning rate, right? So for example, the basic learning rate is scheduling, the RProp, the RMSprop, they are just focusing on the learning rate is scheduling, right? The other idea is to reduce the variance of your move, right? Or your gradient computation. And that one is basically the momentum idea, right? And then the momentum idea has that one. Also, the Atom has that one along with the learning rate is scheduling, right? So these are the 2 classes of ideas that can improve your SGD performance. And Atom has both of them. Now, whatever we have discussed here are what we call it first order optimizer. And what do we mean by that? This means that we only rely on the gradient. Okay? So we only compute the gradient with respect to weights. When you want to optimize, you're only working with the gradient of W, right? You only work with G. You don't go for any higher order gradient, right? The first order gradient only. People sometimes call it gradient-based approaches. But do we have any other sort of optimizer? Definitely. I mean, if you have higher order derivatives, you definitely can do better, right? Because you know more about the function, you know the curvature of the function, other things, and that's going to help you decide better, right? If you have a quadratic function and you do know the Hessian of that function, you can eventually just get to the optimal point in one shot, right? So second order optimizer are significantly better. For example, they use the Hessian, which is the second order derivative. And then if you know the Hessian, instead of using the basic gradient descent, you can use approaches like Newton method, right? And that one is going to take you towards the minimum point much faster, much more efficient. But in practice, we cannot really use it, right? So they have significantly better convergence, but the issue is that they are huge in terms of computation. I mean, gradient itself is a complicated thing for us, right? When the model is huge, then you need to just, compute all of those gradients, meaning that you need to go forward and backward over a very deep neural network. Now, if you want to compute the second order, you need to go forward, backward as much as the dimensions you have, right? Because once you computed the gradient, you need to compute the gradient of every single gradient, right? And this is the second order, right? That's going to be huge. We cannot afford it, right? So in practice, we don't do it really. Like thinking of second order optimization for LLM, this is impossible, right? Because the model is huge. But there are some tricks that people do. For example, they use approximate Hessian. So they don't use the Hessian itself, but they look at the change in the gradient to somehow estimate it, right? This is what we call it pseudo-quadratic approach. They are not going to improve significantly because really you don't have the Hessian, right? But sometimes they can help. So if you see pseudo-Newton, pseudo-quadratic approaches for optimization, they're basically, again, gradient-based, the first order, but they try to somehow get a bit of information about the higher order out of that.